Hey guys, so I'm going to be taking you through a summary of our concept paper, which is titled Contrasted Knowledge Distillation for Banana Leaf Disease Diagnosis Using Sparse Capsule Networks. So let's get started. Basically, this concept paper proposes the development of an AI-driven system that leverages a multimodal approach to automatically detect banana xanthomonas wilt, or you can call it bacterial wilt, from banana leaf images and then provide text-based advice to banana farmers on treatment and prevention strategies. So the system comprises of a multimodal that uses self-supervised learning techniques like knowledge distillation, sparse learning, sparse capsule networks, and these are mainly for higher efficiency and better disease feature learning. And they also cater to some of the computational problems that we mentioned in the concept paper. And I'll be mentioning them as we go on. So some of the keywords that are used in the concept paper to give us an intuitive understanding of what the system comprises of. We have knowledge distillation, contrastive learning, sparse capsule networks, natural language generation, computer vision, deep learning, multi-modeling, convolutional neural networks, overfitting. And some of these keywords are going to be defined as we go on with this summary. So we know that bananas are literally one of the major food energy requirements for many people in Africa. But the problem is that the majority of small-scale banana farmers in Uganda lack expert advice, and they struggle to identify banana disease symptoms, and this delays diagnosis and subsequently leads to substantial crop losses, and this would have a severe impact on their livelihood, especially in Uganda. So technically, this project involves the development of a system that combines two components: a computer vision model that uses optimized capsule networks for image classification and object detection, and a natural language generation model that generates customized advice to these farmers based on the detection results from the computer vision model. So some of the keywords that we've used in our paper, these are the definitions and what they mean for our concept paper. So contrastive learning is like teaching a machine to distinguish objects, and it's a self-supervised learning technique whereby we train a model to differentiate between similar and dissimilar samples. Then knowledge distillation. This is a form of model compression that allows a relatively simple model to perform tasks almost as accurately as a complex model. So in this case, we have a pre-trained teacher model that transfers its knowledge to a student model, and that's how the student model is able to perform tasks almost the same as the teacher model. So then we have sparse learning, which is a technique where models learn from only the most relevant features, thereby reducing computation and improving efficiency, but by eliminating redundant features from the data, redundant parameters. Then we have sparse capsule networks, which are an advanced type of neural network that's used in image classification and object detection. So they are designed to enhance traditional capsule networks by incorporating sparsity into the routing and structure of capsules. So they do that through iterative dynamic routing. So the problem statement, we have the domain-specific problem. That means the problem that we are trying to solve in agriculture. The fact that bacterial spreads rapidly in banana plantations and causes losses, but then most farmers are not able to to detect, to identify these symptoms and signs early. So therefore, it's definitely going to lead to something very bad for them, potentially economic hardships or losses of an entire plantation, dead plants. So we also have problems in data collection, where most people have been using traditional approaches like disease surveillance and scouting, fieldwork visits. And this approach actually lacks the ability to provide precise data on bacterial wilt infections, and this hinders effective management of diseases where bananas are grown. So we also have the computational problem, whereby since our computer vision model consists of a convolutional neural network, but the problem with these convolutional neural network models is that they tend to overfit and they require large training data. And in most cases, they fail to learn the spatial relationships between the features in the given images in the dataset. So another challenge is misclassification that comes with augmentation techniques that we use to reduce the dimensions of the images and trying to avoid overfitting. Then these models also require substantial memory and processing power, and this can lead to increased training times, like increasing that time we need to train the model, and also the need for advanced hardware that is like practically impossible in a resource-constrained environment, like for example, rural areas, because we know most of these banana plantations are located in rural areas. So our proposed solution consists of a multi-model, as I mentioned, which consists of a computer vision model, which will use a sparse capsule network to better understand spatial relationships between leaf textures and symptoms. So this allows us to determine the severity level of the bacterial infection and then classify the diseased banana plants by maybe early, moderate, and advanced stages, even with a limited amount of data. And this is the advantage with sparse capsule networks. They reduce overfitting while maintaining computational efficiency and also reducing the time that we need to train the model. Then the other model is the natural language model, which utilizes natural language processing models like GPT, which are fine-tuned on agriculture data sets. So the purpose of this model is to generate detailed text based on the detected wilt condition and then provide treatment strategies and additional recommendations to banana farmers. So these special hierarchies from the capsule network are mapped to the natural language model so that it generates prevention and treatment steps for the detected condition. So how our proposed system works, the system is accessible to farmers via a web interface such that when a farmer uploads an image of a banana leaf, the image is preprocessed for model input, and the trained capsule network model will classify the image and assign it a severity level. The severity levels, there's early and moderate, and the severe stage where the plant is badly off. So the detection results will then be passed to the natural language model as input, and then it will generate customized advice based on predetermined knowledge and the training data that we give the model. So the system returns both visual confirmation, which are detection results of the infection, and also texture recommendations as output. So what the user will see is an annotated image along with the generated advisory text. So in our dataset comprises of about 1,288 pictures of banana leaves under 3 categories. So there's the healthy category, the banana leaves that are healthy. Then we also have the category of the Xanthomonas infected leaves, that's bacterial wilt. And we also have the Sigatoka infected leaves. So each of these images has an approximate size of about 5 to 6 kbs. And in the next section, we are going to be looking at the exploratory data analysis that we performed on this data set. And we'll be showing you some of the visualizations that we were able to make from the data set to analyze the image properties and features. Thank you.
Hello, my name is Bia Stella. I'm going to be taking you through the contrastive knowledge distillation for banana leaf disease diagnosis using sparse capsule networks. I'll be taking you through its visualizations. As you can see, there's the first one here. That is the sample images. Yeah, the sample images per class. In our data set, we have 3 classes, and that is the healthy, Segatoka, and then the xanthonomas. The first here just represents the images from each class, showing the healthy leaves and those with the various diseases, as I've mentioned. That is the healthy, Segatoka, and then the xanthonomas. And this helps us to visually confirm the dataset's quality and diversity. Then we have the class distribution. This bar chart highlights the number of images per class. In my dataset, there are some imbalances with the images and the more healthy leaves than the diseased ones. This requires strategies like the augmentation to balance the classes during training. Next, we have the aspect ratio distribution. Well, this aspect ratio distribution histogram just shows the dimension of the ratio, shows the dimensions of the images. The uniform aspect ratio are important for resizing without distortion, ensuring spatial relationships in the images remain intact. The next visualization, we have the average image per class. Well, by averaging all the images in a class, we can identify the common patterns that these leaves have. For instance, if there's the healthy one appears uniformly green, then the diseased ones show distinct regions with discolorations and some spots. The next one, we have the grayscale intensity distribution. This shows the pixel intensity range in the grayscale image. It highlights just the important differences between the healthy and the diseased areas, then identifying the texture patterns during model training. Then we have a color histogram. Well, this color histogram, it just visualizes the distribution of the channels. Like the diseased often have distinct shifts in color values, such as yellowing or black spots, which are important features for classification. Then we also have the brightness distribution. All the brightness levels vary depending on the lighting conditions. Well, when capturing these images that are going to be put into the machine learning model, well, standardizing brightness across the dataset ensures the model focuses on disease-related features rather than lighting differences. Then we also have the detection, edge detection. The edge detection, it just highlights structure features like the veins and the infection boundaries. For instance, diseased leaves often exhibit gagged or irregular edges that differ from the healthy ones. We also have the corner detection. Well, the corner detection just identifies that the areas of high variations, such as the spots or sharp transitions. These are critical for capturing disease-specific patterns. Then we have the average per color, or average color intensity per class. By calculating the average color for every class, we can observe general trends. For example, the healthy leaves may have consistent green shades, while infected ones might have like yellow or a tone brown in the leaves. Then lastly, we have the image pixel distribution. This distribution shows the intensities that these pixels have, that the pixel of the it shows the pixel intensities across all the images that will be put. It confirms that the dataset has sufficient contrast between the classes for efficient or effective feature extraction. That is all I had. Thank you so much for listening.